For thousands of years, we humans have loved drawing the outlines and shapes of the world on maps to know where we are and what surrounds us. And in this quest, there is an obsession that has persisted through the ages and still eludes us today, knowing what the shape of the universe is. Often, when we talk about the universe, our minds almost instinctively form a picture of it. A kind of immense, infinite expanse of space that stretches out in all directions, without limit or curvature, without end or boundary, and in which it is possible to keep going on toward infinity. Except you'll see that it's actually much stranger, because the possible shapes of the universe contain some mind-blowing geometric oddities. And it could very well be flat or curved and closed, like a four-dimensional sphere, be finite without edges, or even shaped like a donut, or even folded in on itself and filled with optical illusions that make it appear larger than it actually is. And many, many other things as well. That being said, let's get back to our hallucinatory geometric journey by starting with a little thought experiment. Imagine that you have a spaceship equipped with futuristic technology, and that it can travel much faster than light. Armed with this incredible machine, you decide to set out to explore the universe, always moving straight ahead, never stopping. Determined to reach the limits of the space around us, to go to the edge of the universe. Your futuristic ship allows you to break free from the speed limits imposed by the laws of nature. You quickly leave the solar system, then our galaxy, surpass our local galactic cluster and the neighboring superclusters of galaxies, rapidly moving farther from your starting point. After spending ages watching countless universes pass, you see in front of you a cluster of galaxies that looks strangely familiar. Continuing to go straight ahead, you get closer and realize that you're facing our galaxy, the Milky Way. And as you keep moving straight ahead, a few moments later, you find yourself facing our planet. You have come back exactly to where you started, even though, throughout your journey, you never changed your course or turned back. What this little story tells us is that the universe as a whole can have a global geometry that is radically different from what it seems to have to us, at the scales at which we observe it, and that the shape of the entire universe can have mind-blowing consequences, like coming back to your starting point after traveling for a small eternity in a straight line. When we try to determine the shape of the universe, the first thing to do is to try to measure the curvature of space on very large scales. Because for more than a century now, we have known, thanks to the work of Einstein, that the geometry of space, its shape, is directly related to its contents, to the amount of mass and energy that are present in it. Because it's this density of matter and energy that dictates the curvature of space. So, like this, it might seem complicated, but actually, it only leaves three possibilities. Either the curvature of space is positive, negative, or zero. And each of these possibilities has absolutely mind-blowing consequences. If the universe has a matter-energy density that exceeds a certain critical threshold, space must be, on very large scales, slightly positively curved, just like the surface of a sphere. In such a universe, no matter which direction you go in a straight line, if you can travel faster than the universe is expanding, you inevitably end up coming back to your starting point. This is called a closed universe, even though it has no physical edges or boundaries that are impossible to cross. Do you feel like I do that it's starting to itch? The idea seems completely paradoxical at first glance. To understand why such a universe has finite space but remains limitless, we can use the analogy with our world, the Earth globe. We live on the surface of a sphere whose extent is finite but has no boundaries. On the surface of the Earth, you can walk in a straight line indefinitely without ever encountering an edge. But you will inevitably end up coming back one day to the exact point where you started. Second scenario. If the universe has a matter-energy density below the critical threshold, then space must be, on very large scales, negatively curved and have a hyperbolic geometry. To try to imagine how space bends in this way, think of the shape of a saddle surface. And in such a universe, which is called open, if you can travel faster than the universe expands, you never return to your starting point, because no loops form there. Space keeps escaping there, because an open universe is literally infinite. Finally, the third and last scenario. If the matter-energy density of the universe is exactly balanced, then the curvature of space is zero. Even at very large scales, no inflection appears on the horizon, and the geometry of space is perfectly flat. In such a universe, two photons of light traveling side by side in a straight line remain parallel for eternity. And where it gets fascinating is that the value of the curvature of space touches on something fundamental. It determines not only the possible paths that can be taken, but also how the universe will evolve. And it gives us clues about the fate of the entire cosmos, about how everything will end. Because each of the three geometric possibilities we've looked at, closed, open, or flat universe, has its own destiny, and each one is, in its own way, a little frightening. In the case of a closed universe, the real drama isn't that any path followed long enough in the same direction, moving faster than the universe expands, will inevitably loop back on itself. After journeying through much of the cosmos, any cosmic traveler returns to their starting point. But that such a universe is doomed to inevitably collapse in on itself. Because the fate associated with this geometry is one where gravity eventually overcomes expansion, managing over very long periods to slow it down and then to stop it completely, before reversing it and forcing the entire universe to contract in on itself. In a kind of reversed Big Bang, a big crunch where all matter and energy eventually return to a compressed state. At the other extreme, if we are in an open universe, meaning that the density of matter and energy is unable to counterbalance the expansion that prevails. On gravity, then, the final fate of the cosmos is not to close in on itself, ending up as a compact furnace at staggering temperatures, but rather one of perpetual cooling, with space-time stretching endlessly in all directions. In short, the fate of a hyperbolic space is one of infinite dilution of matter and energy within an ever-expanding universe, darker, colder, and where absolute silence reigns. Atmosphere. Finally, there's a third possibility, a universe balanced between these two extremes. A universe whose matter-energy density is exactly equal to 1 and where the curvature of space is 0. In that case, the cosmos is unable to contract and reduce its volume. The Big Crunch scenario is then ruled out. And the future of this type of flat universe depends on its behavior over very long periods of time and on the exact nature of the mysterious force that is currently accelerating cosmic expansion, dark energy. But to sum up in broad strokes, let's say that here too, the future is heading toward perpetual cooling and dilution. What is the universe's shape, and which of these three scenarios is correct? All the difficulty in answering this dizzying question comes from the fact that the universe doesn't let us see its shape directly because we're trapped inside it. There is no distant observation point that would allow us to take it all in at a glance, to see it entirely from the outside. So how can we be able to draw the true face of the cosmos on very large scales? We have to rely on the clues that light gives us and decipher how its propagation has evolved over time. Because each possible geometry of the universe affects the way light travels through it differently. You'll see, it's fascinating. Let's take a very concrete example. At the scales we're at, like in a flat universe, parallel lines remain parallel forever, without ever meeting or diverging. The sum of a triangle's angles, or three connected points, is always 180 degrees. But in a universe where space on large scales isn't flat, none of that is true. Take a balloon and draw a triangle on it. If you're a child, ask your parents for permission first. If you're a parent, ask your child for a balloon first. As I was saying before I interrupted myself, the surface of a balloon is like the Earth's surface. The sum of the angles of a triangle is greater than 180 degrees. Quite simply, because the surface is curved. If you draw a triangle on a saddle, first ask your horse's permission. Well, you'll find that the sum of these angles is this time less than 180 degrees. And that's absolutely brilliant, because that means the curvature of space must be observable at the very large scales of the universe. So astronomers have been probing what's called the cosmic background radiation for decades now. This luminous remnant is from the universe's earliest moments and fills the cosmos. And in it, they try to detect fluctuations that would indicate the curvature of space. And the puzzling verdict is, the tiny variations we observe in the deep sky tell us that the light reaching us has traveled in a straight line for nearly 13.8 billion years. And so the universe seems perfectly flat. And that's with an extraordinary degree of precision in the measurements. And that's absolutely puzzling because it raises a profound question. Why does our universe have such a particular configuration? How can we explain that among all the possibilities it seems to contain just the right amount of matter and energy for space to be flat? Is it the result of an incredibly suspicious coincidence or the consequence of something that was precisely tuned from the very beginning? This puzzle, which remains one of the greatest unsolved mysteries of modern cosmology, is known as the flatness problem, which is a polite way of saying that we don't know why the universe is like this. After all, the fact that space is, on large scales, devoid of curvature is good news. If the big crunch frightens you. Because a flat universe rules out the fate of cosmic bellows collapsing into gigantic spheres that shrink entirely into a ridiculously small point. Except that this is where it gets a bit complicated. It's that even though the vast part of the universe we can observe appears so flat that it would make a Breton pancake look thick, for the Swiss Alps, it's not impossible that its true shape is hidden from us by its extraordinary dimensions. In the same way that on the surface of the ocean, the horizon seems flat to you because the stretch of landscape you can take in at a single glance is insignificant compared to the size of the object you're standing on. So, it's entirely possible that our universe, which appears flat to us on a small scale, so by small scale we mean distances of several billion light years, actually has a globally curved geometry. And to understand why, a little refresher. Okay, a big shot is in order. We can currently only observe the part of our universe whose light has had time to reach us. Since the universe has existed, what we call the observable universe, but this observable universe is probably only a tiny fraction of the total universe, beyond the limits of our current view. It forms a sphere centered on Earth. With a radius of 46 billion light-years, it is impossible for us to see, because the light beyond this limit has not yet had enough time to reach us. Since the universe has existed, if the 46 billion light-years radius seems absurd to you, I refer you to this video. And beyond this limit, which we call the cosmological horizon, there very likely still exists more of the universe, with billions of galaxies and space in all directions. We are limited observers, trying to deduce the shape of a vast puzzle, most of which is inaccessible, and of which we see only a tiny fragment. So, being flat locally does not necessarily mean being flat globally. We cannot be certain that the universe as a whole has a perfectly flat geometry, because it's possible that space has such a slight curvature that it cannot be measured. In other words, this gigantic observable universe, with its 93 billion light-years in diameter, might actually be too small compared to the size of the entire universe to allow us to measure its curvature. And it's entirely possible that space is actually very slightly curved, but on a scale that's too large for us to detect. And where cosmologists are really strong is that even if our observable universe is most likely just a fragment of the total universe, they are able to estimate the minimum size the entire universe must have for its curvature to be impossible for us to detect. So, given the maximum curvature allowed by our measurements, the entire universe would be at least 250 times wider than the observable universe. But that's the lowest possible estimate. And by giving space an absurdly tiny curvature, it could just as well have a volume 15 million times greater than what we can see. In short, we're like fish trying to guess the size and shape of the ocean without being able to leave their little aquarium. And the only thing we're certain of is that if space is curved, the entire universe must be extraordinarily vast to hide it from us. Unless the universe has a topology that hides its true shape from us. Now let's make things even stranger. Because while the curvature of space is a property of the universe that can be measured directly without leaving it, topology is not. It is a global property that tells us how space connects on a large scale without its curvature being affected, and which cannot be seen directly from the inside. So being able to visualize the shapes we're going to talk about in 3 dimensions without having the powers of a hypothetical God observing the universe from the outside. And it's a challenge even for specialists. And for you and me who are inside the universe. Let's, in the next few minutes, feel reality slip out from under our feet. But hang on, it's worth it. I promise you that after stretching a few neurons, we'll end up finding our balance again. Let's start by remembering this. The fact that space is flat doesn't tell us anything about the overall size or shape of the universe. A shape that's impossible to draw on paper because it includes more dimensions than we can represent. Besides, you wouldn't know how to start drawing. Because the universe isn't an object in space. The universe contains all of space itself. And its topological shape isn't just an outline, it's a fundamental property of reality. Okay, that's where I got lost, to try to get a sense of how much complexity topology adds. Imagine that you're shrunk down to the size of a bacterium and placed in one case on the surface of a balloon, and in the other on the surface of a donut. So miniaturized to the extreme, and in both cases, the surface you're moving on seems flat to you. But if you keep moving straight ahead, after a while, you'll end up coming back exactly to your starting point. From your perspective, you've always moved in a straight line. The fact that you end up exactly where you started would be irrefutable proof that the surface you're on is actually very, very slightly curved. But that doesn't allow you to know whether you're on the surface of a sphere or a donut. To be able to decide, you would need to pull yourself out of the object you're on and observe it as a whole. In other words, for a bacterium, a balloon, a cylinder, or a donut are all spaces without limits or boundaries, which are both finite in volume and without edges, while being locally flat. In other words, all these shapes have the same local characteristics, but their topologies are radically different. And these are the simplest possible examples. When we move to the scale of an entire universe, the varieties of shapes that are locally flat and hide global geometries as complex as they are surprising are simply dizzying. In fact, if the space of the entire universe is even slightly curved, then the possible topologies are literally infinite in number. And since we don't have all eternity ahead of us, so we're going to set these scenarios aside and consider that space is perfectly flat, as the measurements seem to indicate. In which case, the global shapes of the entire universe are reduced to only 18 possibilities. Some are twisted, others folded in on themselves, or have unexpected loops of hidden connections, when they don't have distorted faces but are connected to each other. 8 of these topologies even have a very strange feature. They are non-orientable, like a Mobius strip in 3 dimensions. They contain closed paths that, if you follow them long enough, will bring you back to your starting point, but with a reversed orientation, in a universe with these strange global shapes. By always moving straight ahead and faster than the speed at which the universe expands, you would eventually return to your starting point, but with a mirrored, reversed orientation. That is, all your organs would have switched sides. Your right side moles would be on the left and left side moles on the right. And your home planet would appear to you like Earth seen in a mirror, while its inhabitants, from your point of view, would have their hearts on the wrong side. Though fascinating in theory, these non-orientable universes cause many consequences that have never been seen. Therefore, these global shapes have been ruled out. That leaves us with only 10 topologies of perfectly finite and borderless universes, 10 possible shape candidates for the universe. I'm not going to go into detail about all of them, because each of these shapes has its own peculiarities, and above all, most are so complex to represent that they crumple and twist the brains of non-experts like me into some kind of wild origami, just trying to picture them mentally. Just keep in mind that all the images appearing on the screen are mainly there to illustrate the journey and evoke its diversity, to give you something visual to hold on to. But none of them correspond exactly to what we're talking about, to make you experience the subtle, unusual consequences and the subtle effects these topologies can cause. We're only going to focus on 2 of these possibilities, which, as you'll see, are already going to blow our minds. Starting with the shape that is probably the most delightful and the most popular of all, namely the donut-shaped universe, also scientifically called a toroidal universe with multi-connected spaces. In such a universe, space is intrinsically flat and you could move forward without ever encountering an edge. Because you have to keep in mind that the larger plane of space, which gives us the 3D donut shape in these images, doesn't actually exist. The only possible point of view is that of an observer located inside. So, as strange as it may seem, if you go far enough in any direction, you inevitably end up on the opposite side, on the other side of the donut. A bit like those video games where the space is finite but without any edges. That makes you reappear on the other side of the screen when you go past the frame's edge. So don't worry, if your brain is screaming at you to reject this idea, that's normal. We're not wired to easily picture the peculiarities of a toroidal space. By the way, in the 3-dimensional space we live in, it's impossible to build a true torus without deforming the material used to make it. But in this strange topology, it's the entire universe that's mapped onto the surface of the donut, which means that in a completely counterintuitive way, it has neither curvature nor edge. And where it gets really interesting is that a universe with such a shape has consequences. From inside a universe with the topology of a donut, the volume of space around you is not infinite. So, if you are in such a universe and it is old enough for light to have had time to travel all the way around it, then, by looking all around you, you should be able to see many images of the galaxy you live in. Because the rays of light that left it then followed many different paths for colossal amounts of time until they returned to their starting point. In other words, in a sufficiently old toroidal universe, infinity is only apparent. It's an illusion caused by the repetition of images produced by a limited number of galaxies, whose rays of light follow paths that are actually disguised circles, allowing the light to return to its source. So far, no signature of these repeated images has been detected in the sky. This suggests the universe's topology isn't that of a donut, unless it's too large for light to have had time to make a complete circuit around it. However, in the early 2000s, researchers noticed an anomaly while studying the cosmic background radiation, in which they realized that there seems to be an almost complete absence of certain large resonance wavelengths, as if the universe were actually smaller than what we can observe and therefore unable to contain certain vibrations. Just like a guitar string that cannot produce a sound lower than what its length and diameter allow. And to explain this strangeness, Jean-Pierre Luminet and his colleagues suggested that the universe has a crumpled shape, or, if you prefer, a topology of dodecahedrons made of square points. A strange shape made up of 12 pentagonal faces, like some dice often used in role-playing games. Except that the faces of this crumpled topology have the strange property of being connected. And if you were able to reach one, you would instantly come out through the opposite face after performing a sort of rotation. This may seem completely far-fetched to you, but on the crumpled paper, this kind of hall of mirrors with images coming from several directions is perfectly plausible. And its existence would suggest the universe's total volume is 120 times smaller than that of the observable universe. Because the immense variety of galactic structures we observe in all directions could be born from the multiplied images of a small number of them, whose light, after moving through this universe's strange faces, we would see them from different angles and at different periods of their history. In any case, it's a hypothesis, a possible topology among many others, each with its own consequences. So, researchers continue to meticulously examine the cosmic background radiation and the distribution of galaxies in space in an attempt to detect mirages. Repetitions of images of the same object, seen multiple times and in different directions, and whose discovery could reveal the existence of an astonishing topology. But nothing conclusive has been found yet to settle the matter. Which doesn't mean that our universe doesn't have a strange, multi-connected shape. Maybe the repeated images are drowned in cosmic noise, or they're beyond our observable horizon, in a part of the universe that we will never be able to see. In short, we're not out of the woods yet. In fact, we're still stuck inside. That doesn't stop us from marveling at the fact that somewhere in this vast and strange universe, a species forced to study the sky from its little planet managed to develop instruments and equations, allowing us to study its incredible potential forms. Admit it, we're not doing so badly for fish trapped in a bowl. In any case, I hope this dive into the enigma of the shape of the universe has changed the shape of your brain a little, which in itself would already justify the journey. And what if it turns out that one day we discover that we actually live in a gigantic donut? I won't fail to keep you posted, hoping it's cinnamon flavored.